Alright, so I'm going to be showing the solution to problem number 16 in chapter 37. So the problem is as follows. Space pilot Mavis zips past Stanley at a constant speed relative to him of 0.800 times c, which is the speed of light. Mavis and Stanley start timers at 0 when the front of Mavis' ship is directly above Stanley. When Mavis reads 5 seconds on her timer, she turns on her bright light under the front of her spaceship. Now there is three parts to this. The first part is part A, and it says, use the Lorentz coordinate transformation derived in example 37.6 to calculate x and t as measured by Stanley for the event of turning on the light. Alright, so we have to calculate what Stanley measures for x, or his position, how far away the event of the light turning on is, and also what Stanley measures for time. At what time does the light turn on? So, part A, I have to use those Lorentz transformations. And the equations for this Lorentz transformation for x is equal to gamma times x prime plus u t prime. Alright, so let's find Stanley's x. Alright, so this is Mavis's x, what she experienced position, but from like her frame of reference, there isn't really one. It's just the distance. It's not like measuring the spaceship at all. It just says from this. So this simply it just goes to 0. All right. So then Stanley's x simplifies down to gamma times u t prime, and t prime is Mavis's time, which is given to us. All right, so now we just plug in the variables or the values that are given to us. So x for Stanley equals, let's see, 0.800 c. C again is the speed of light, times Mavis's time, which is 5.00 seconds, all over, because gamma is 1 over square root of 1 minus u squared over c squared, all over 1 minus 0.800 c squared, all over c squared. And then if you just solve for all these values, just evaluate this equation. Remember, c is not a variable, c is a constant, c is the speed of light, which is 2.998 times 10 to the 8th meters per second. And if you're to plug all these values in and you keep track of significant figures, it should come out to be Stanley's measures his distance from him to the light turning on. He measures it to be 2.00 times 10 to the 9th meters. Alright, so that's Stanley's x. Now we need to find Stanley's t. Alright. So Stanley's t, so we're going to be using the time Lorentz transformation equation. Time for the Lorentz transformation is equal to gamma times t prime plus ux prime all over c squared. Alright. Alright, so looking at this equation, we already know, we have already decided that x prime is just 0, so this whole thing just goes to 0. So then Stanley's time is just gamma times t prime, which goes to t equals Mavis's time, which is 5.0, all over the square root of 1 minus 8.800 c squared all over c squared. All right, and again, so in these equations, right here, this value is supposed to be u squared, and u is the speed of Mavis in this situation. So we take Mavis's speed, which is 0.8 times c, and c is the speed of light, and plug into that equation. So then if you were to evaluate this and keep track of significant figures, Stanley's time for when the event happens, for when the event of the light turning on happens, he measures that to be 8.33 seconds. Okay, so this is it for part A. We found Stanley's time, and then we found Stanley's position. All right, so now let's move on to part B. Okay. All right, part B. Use the time dilation formula, which is T equals gamma times T prime. Use the time dilation formula, let's see, to calculate the time interval between the two events, the front of the spaceship passing overhead and turning on the light, as measured by Stanley. All right, so the time interval is, so for Mavis, her time interval for between starting her spaceship, or like from the event once her flying over Stanley to the light turning on. And from her perspective, the light turns on at, so it was 5.00 seconds. Okay. All right, now it says find Stanley's time interval. So what I have to do is just convert it. So remember, Stanley's initial time is also just 0. And now for this one, we convert this one to Stanley's time using this equation. So it would be 5 seconds times gamma, which is 5 over the square root of 1 minus 8.8 times c squared over c squared. Just the standard equation for gamma. Which again, 1 minus u squared over c squared, and just plug the values in. Remember, u squared is Mavis's speed, which is given to us. That's the speed of light. And so if you were to plug that in, the answer would come out to be 8.33 seconds, like we got in the previous problem. All right. Stanley, and it says compare this value of t to what you calculated in part A, and this value, it's the same as what was calculated in part A. All right, now C. It says multiply the time interval by Mavis's speed, both as measured by Stanley, to calculate the distance she has traveled as measured by him when the light turns on. So basically it's just saying we take Stanley's time and multiply it by her velocity to get the distance she travels since like she passed over him. And so it would just be, and again, of course, remember with this you have to keep track of sig figs. So again, if you were to just do 8.33 seconds times Mavis's speed, which is 0.800 c, and if you were to keep track of sig figs, this answer would come out to be 2.00 times 10 to the 9th meters. Okay, all right, and if you may notice, this is the same value of x that we got in part A, 2.00 times 10 to the 9th meters. And let's see, that is it for problem number 16, chapter 37.